Now let's take an example. Suppose that our hash function converts a two-digit integer input into a single-digit output by taking the least significant digit. The least significant digit is basically the rightmost digit. So that is the hash value what the function will return. Let's pick an example where we will insert the numbers 81, 70, 97, 60, 51, 38, 89, 68, and 24 into the initially empty hash table, where hash table of size m equals to 10. Now the size of the hash table is not a prime number, it is picked just for demonstration. Inserting 60 causes a collision in bin 0, since the cell is already taken by 70. Therefore, we check by moving forward and find bin 1, which is full. It is occupied by 81. Thus we move forward and check bin 2, which is empty. Thus we put 60 into bin 2. Inserting 60 causes a collision in bin 0, since the cell is already taken by 70. Therefore, we check by moving forward and find bin 1, which is full. It is occupied by 81. Thus we move forward and check bin 2, which is empty. Thus we put 60 into bin 2. Inserting 51 also causes a collision, this time in bin 1, which is occupied by 81, since the least significant digit of 51 is 1. Therefore, we check bin 2 by moving forward. Bin 2 is also occupied by 60. Moving forward further and checking bin 3, we find it empty. Thus we put 51 into bin 3. 38 and 89 can be placed into bin 8 and 9 respectively without collision, since the bins are empty. Inserting 68 causes a collision in bin 8, since it's occupied by 38 and the least significant digit of 68 is 8. Therefore, we move forward and check bin 9, which is taken by 89. To move forward, we do a wraparound and go to bin 0, which is taken by 70. Moving further forward to bin 1, which is taken by 81. Again moving forward to bin 2, which is taken by 60. Moving forward to bin 3, which is taken by 51. And finally moving forward to bin 4, which is empty. Thus we insert 68 into bin 4. Inserting 24 causes a collision in bin 4, since the least significant digit of 24 is 4. However, next bin, which is 5, is empty where it can be placed. Testing for membership is similar to insertions. Start at the appropriate bin and continue searching forward until either the item is found or an empty bin is found. Searching for 68, whose least significant digit is 8, we first examine bin 8 where it's not present. Then we move forward and check bin 9 where it is not available as well. Further we move to 0, 1, 2, and 3, and finally finding 68 in bin 4. Now searching for 23, we will gonna search bin 3 since the least significant digit of 23 is 3. It's not present there. We move forward to bin 4, bin 5, and finally when we check bin 6, it's empty. Since empty bin is used to terminate search condition, thus 23 is not available in the table. We cannot simply remove elements from the hash table since empty bins are used to terminate search. For example, if we delete 89 by removing it, we can no longer find 68 since bin 9 will be empty once 89 is deleted. By deleting 89, however, we cannot simply move all entries up to fill the gap created by deleting 89. Moving 70 to bin 9 would make it impossible to find 70. Instead, we must probe forward, moving only those elements which would not be moved to a location before the bin starts. For example, we remove 89. We removed 89 which was at bin 9. We probe forward going from index 9 to index 0 until we find an entry which can be moved into bin 9. We cannot move 70, 81, 60 or 51, but we can move 68 since 68 checked bin 8, then 9, then 0, then 1, then 2, then 3, and finally bin 4 where it was inserted. Due to 68 checking bin 9, we can pick 68 from bin 4 and drop it in bin 9. Next, we search forward again, moving only those elements which would not be moved to a location before their bin starts. And note that 24 can be moved forward since 24 checked bin 4 and then bin 5 where it was inserted. Thus, we can pick 24 from bin 5 and drop it in bin 4. The next cell, which is bin 6, is already empty, and therefore we are finished. Suppose we now remove 60. We find 60 in bin 2, and therefore we can remove it. We search forward and find that we can move 51 into bin 2 since 51 checked bin 1, then 2, and finally bin 3 where it was inserted. We cannot move 24 forward because it's already put into the least significant digit bin. The next bin 5 is empty, therefore we are finished. For primary clustering, we have already observed the following phenomena. As we insert more elements into the hash table, the contiguous regions get larger. In other words, blocks of data are forming when collisions are resolved. This is known as primary clustering. Any key that hashes into the cluster will require several attempts to resolve the collision, and once resolved, will be placed at the end of the cluster, making the cluster even larger. This results in longer search times. Consider inserting the following entries: 81, 70, 97, 63, 76, 38, and so on and the last digit is 49. Use the number modulo 25 to determine which bin it should occupy. The first 5 do not cause any collisions. For example, 81 mod 25 gives us 6. Therefore, we insert 81 into bin 6. Similarly, 70 mod 25 gives us 20. Therefore, we insert 70 into bin 20. 97 mod 25 gives us 22. We insert 97 into bin 22. Then for 63 mod 25 gives us 13, and we insert 63 into bin 13. And the fifth one is the 76 mod 25, which equals 1. Therefore, we insert 76 into bin 1. Inserting 38, whose hash value is calculated as 38 mod 25, which equals to 13, causes a collision in bin 13, which contains 63. Thus, we move forward and insert it in bin 14. Now, the next 7 values, which are 85, 68, 21, 9, 55, 73, and 57, do not cause any further collisions. Let's do the remainder method and insert the entries. 85 mod 25 is 10. Therefore, we insert 85 into bin 10. 68 mod 25 is 18. 68 gets inserted into bin 18. 21 mod 25 is 21. We insert 21 into bin 21. 9 mod 25 is 9. Gets inserted into bin 9. 55 mod 25 is 5. We insert it in bin 5. 73 mod 25 is 23, so it gets inserted in bin 23. 57 mod 25 is 7, therefore we insert 57 into bin 7. Inserting 38, whose hash value is calculated as 38 mod 25, which equals to 13, causes a collision in bin 13, which contains 63. Thus, we move forward and insert it in bin 14. Now, the next 7 values, which are 85, 68, 21, 9, 55, 73, and 57, do not cause any further collisions. Let's do the remainder method and insert the entries. 85 mod 25 is 10. Therefore, we insert 85 into bin 10. 68 mod 25 is 18. 68 gets inserted into bin 18. 21 mod 25 is 21. We insert 21 into bin 21. 9 mod 25 is 9. Gets inserted into bin 9. 55 mod 25 is 5. We insert it in bin 5. 73 mod 25 is 23, so it gets inserted in bin 23. 57 mod 25 is 7, therefore we insert 57 into bin 7. The remaining insertions all cause collisions as well. 61 mod 25 equals 11. Bin 11 is already taken by 60. Once we take it forward, it will be inserted in bin 15. Similarly, 7 mod 25 equals 7. Bin 7 is taken by 57, and it will be inserted in bin 8 once we take it forward. 49 mod 25, which equals 24. Bin 24 is taken by 72, and it will be inserted in bin 2 once we take it forward. For asymptotic performance of open addressing linear probing, primary clustering affects the number of probes required to perform the insertions, searches, or deletions. The average number of probes for a successful search using linear probing can be estimated as follows. Your number of probes is approximately equals to 1/2 times 1 plus 1 divided by 1 minus lambda, where lambda is number of elements divided by the table size, and it's called the load factor, which implies what fraction of the table is used. Further to the asymptotic performance, the number of probes for an unsuccessful search or for insertion is higher. So for that, the number of probes is approximately equals to 1/2 times 1 plus 1 divided by 1 minus lambda to the power of square. Now if your load factor is around 0.75, then 8.5 probes are expected. If your load factor is 0.9, 50 probes are expected, and this is unreasonable. So in nutshell, if load factor is too small, then you will have too many empty entries than stored entries in the array or in your hash table. If load factor is too large, clustering will happen and hash table will become inefficient. So the typical choice will be for the load factor to be 0. 0.5, which implies 2.5 probes are expected then. Linear probing can be a bad choice if the table is more than half full. The following plot shows how the number of required probes increases. You can observe the plot where the load factor is your abscissa and number of probes is your ordinate. Load factor should not exceed 0.5 for unsuccessful search. For successful search, you can grow the load factor to 0.7 or 0.8 or so. But since successful and unsuccessful search goes in hand together for the algorithm, your load factor should not exceed 0.5. Performance will degenerate or degrade rapidly as the load factor approaches 1. Primary clustering occurs with linear probing because of the same linear pattern. If a bin or a cell is inside a cluster, then the next bin or cell must either also be in that cluster or expand the cluster by being placed at the end of the cluster. This is due to the element's tendency to cluster around hash table locations that they originally hashed to. As long as the hash table is big enough, a free cell can always be found, but the computation time to do so can get large. Not only that, but any key that hashes to the same cluster will require several attempts to resolve the collision, thus putting further overhead on computation time before it's added to the cluster. Instead of searching forward in a linear fashion, consider searching forward using a quadratic function which eliminates primary clustering problem of linear probing, which will be covered in our third online lecture.